Hello, this is Qiu. Welcome to my presentation titled as Privacy Preserving Distributed Expectation Maximization for Gaussian Mixture Model using Subspace Perturbation. This is a joint work with Yaron Skofstad-Gunthersen, Katrina Tina, Rafał Winnicki, and Max Grisbo-Christensen. I will follow this agenda to get you through the presentation, and now let's start with the motivation. Privacy is becoming more and more important, and many countries have their own privacy regulations, for example, the GDPR. And I would like to emphasize that addressing the privacy issue in the context of decentralized system is quite challenging, because this decentralized nature of the system require information exchange between different participants. And this information exchange might reveal sensitive information of individual privacy. Having introduced the motivation, now let's go to the problem setup. First, a bit fundamental of GMM and EM algorithm. Consider a network with n nodes, and each node has its own private data xi. And these nodes want to collaborate together to learn a Gaussian mixture model based on all of their data, where the function is given by here. Let me introduce you the notation one by one. So here C denotes the total number of Gaussian models, and the beta J denotes the so-called mixture coefficient for model J. And this term denotes the PDF for Gaussian distribution with mu and covariance, with mean and covariance mu and sigma. So to update the parameters for the GMM, we can use this expectation maximization algorithm, where in the each step, its goal is to update the conditional probability that Xi belongs to Gaussian model J. So in the M step, it try to use the conditional probability and the Xi to update the parameters for the Gaussian mixture model, namely the mixing coefficient beta, the mean mu, and the covariance matrix sigma. If we take a closer look at this updating function, we can see that in the each step, the updating can be computed locally because it does not require any information exchange across the nodes, so it does not impose any privacy concern. While for the M step, we can see that we have this summation term, which it requires to sum over from node 1 to node n. So it means that we need to aggregate information across the network in a decentralized way, which require information exchange between different nodes, thereby imposing privacy concern. When talking about privacy, the so-called adversary model is very important because it defines what kind of security attacks is being considered in the network. So here we consider two kinds of models. The first one is the well-known eavesdropping adversary. It works by listening to the communication channels over the network to infer the private information. The second model is the so-called passive or semi-honest or honest but curious adversary model. It classifies the nodes into two different kinds. One is the so-called corrupt nodes, and the rest are the so-called honest nodes. It assumes that these corrupt nodes, which means that they are byte nodes, they follow the protocol, but they will share information together to infer the private data of the rest honest nodes. We summarize that there are mainly two requirements to satisfy when designing privacy-preserving distributed EM algorithm for Gaussian mixture modeling. The first requirement is about privacy. Throughout the whole algorithm execution, we would like that each node's local private data Xi should be protected from being revealed to the adversaries. The second requirement is about accuracy. We would like that the estimated parameters for Gaussian mixture model should be identical at the known privacy-preserving counterpart. So, federated learning is very popular as it is motivated from privacy concern because it does not transmit the local data or the private data directly, but transmitting the intermediate updates or results. So in this setting, if we simply apply federated learning, then we can see that we can define this A, B, and C as the intermediate updates for updating the Gaussian mixture model parameters. But however, if we look at look at this intermediate updates information theoretically, we can see that this A and B is using this A and B, we can directly infer what is original private data xi. So information theoretically speaking, the mutual information between the original private data and the intermediate updates is maximum. So we just with this simple example, we just want to emphasize that simply applying federal setting does not always guarantee privacy. So existing privacy-preserving distributed EM algorithm can be broadly classified into three types. The first one is homomorphic encryption approach. Its main disadvantage is that it is computationally complex. The second type of approach is differential privacy approach. It is very general and offers quite strong privacy guarantee, even under the worst case, but it has a trade-off between privacy and accuracy. The last type is the so-called secure summation approach. Its main advantage is that it preserves perfect accuracy, but it needs to first detect the so-called Hamilton cycle for applying this secure summation algorithm. And another disadvantage is that it's vulnerable to security attack when consider a number of passive corrupting nodes. All right, now let's go to the proposed approach. Just now we mentioned that directly transmitting the intermediate update will violate privacy. To solve this issue, we first remarked that by computing the average of all these intermediate updates, we can update these parameters for the Gaussian mixture modeling. For example, the mixing coefficient beta is actually equivalent to the average of all the Aij over the network. So similarly, we can use the average of all the Bij of the network divided by the average of all the Aij of the network, then we can update the mean mu. So similarly, we can update the covariance sigma. So the problem then reduced to how can we securely compute the average of all these intermediate updates over the network in a decentralized way. To do so, we first model it as a distributed convex optimization problem, where here xi denotes the local private data we want to protect, and yi denotes the optimization variable of node I. So the goal is to jointly minimize the sum of all the local objective function, which is the quadratic term over the network, with the constraint that all the yi and 1j of the network should be identical. So the optimal result for the optimization variable yi is equivalent to the average of all the local data si. So there are many distributed optimization algorithms can be used to solve this distributed average consensus problem. Here I just use this PDMM as an example to illustrate the main idea. This is the updating function for PDMM. Let me introduce the notations. So here, each edge in the network, for example, here, for this graph, we have five nodes and 6 edges. For each edge, we introduce two dual variables, lambda ij for node I and lambda ji for node j. So this is why the dimension of this lambda is twice the number of nodes of the edges in the network. I'm sorry. And C is a constant for controlling the convergence rate. And here Bij is relevant for the graph instance matrix. Here we define that Bij equal to 1 if I is bigger than j. It is -1 if I is smaller than j. Of the privacy-preserving distributed average consensus problem, we choose to use the subspace perturbation approach. The main reason is that it is proven to achieve the minimum information leakage, given the condition that perfect accuracy is being preserved. Another advantage is that it is very simple and easy to implement. Now let's look at the main idea of privacy preservation. If we look at the updating function for the optimization variable, we can see that it is essentially a scaled version of the sum of private data and the information collected over its neighborhood. So here Ni denotes the set of all the neighboring nodes of node I. We can rewrite this function into this one, where the left-hand side is all the information which is with all the terms that is unknown to the adversary. For example, here NIH denotes the set of unleased neighboring nodes of node I. Similarly, the NIC denotes the set of all the corrupted nodes of node I, or corrupted neighboring nodes of node I. So in order to analyze the privacy, we should first understand the convergence property of this dual variable. It is shown that this dual variable is actually working on this bipartite graph, where we have twice the number of nodes and twice the number of edges. And the instance matrix of a graph is always rank deficient. So we denote H as the subspace constructed by the instance matrix of the bipartite graph. And based on this, we can always decouple the dual variable into the projection into the subspace H and the projection into its orthogonal complement. So again, coming back to this term, we can see if we look at it information theoretically, where the uppercase denotes the corresponding random variable. So the mutual information between Si and the summation term of Si and the dual variable over the unleased neighborhood, we can decouple this term into the projection into H and the projection into orthogonal complement. And this term, the projection into the orthogonal complement, we denoted as subspace noise. And it is shown that this subspace noise will not affect, no matter how big it is, it will not affect the convergence of the optimization variable, which means that it does not affect the accuracy of the algorithm. So we can make it infinitely large, or as large as possible, to make this mutual information to be asymptotically zero. So this mutual information is can be made infinitely small, such that the privacy is being protected. So again, we remark that the privacy can be guaranteed that as long as there is one unleased neighbor. It means that the set of the unleased neighbor of node I should be non-empty, which is a very mild condition. Just now we have shown the information theoretical analysis of privacy with a single distributed average algorithm. Now for the overall privacy preserving distributed EM algorithm, where in each M step we apply a privacy preserving distributed average consensus problem. So now we need to collect all the information together to see the overall information leakage of the whole distributed EM algorithm. So we summarize that the overall information leakage of the proposed approach is that the adversary only knows the partial sums of all the intermediate updates of the unleased nodes. Let me give you one example to explain the main idea. So imagine we have a graph with 5 nodes and they are connected with each other, and we have 2 nodes, 2 out of 5 are corrupted. Node 2 and 4 are corrupted. If we remove these 2 nodes and the rest 3 nodes, we can see that they form a connected subgraph. So we see that the information leakage of our proposed approach over this graph is that for each node, for every unleased node 1, 2, and 4, the information leakage is contributed by the sum of all the intermediate updates for the sum of all the intermediate updates of unleased nodes from 1, 3, and 5, which is contributed by this set. To have a better idea of how does this outperform the existing approach, the existing secure summation approach, we show that the information leakage of the existing approach is bigger than our proposed approach, because it reveals all the information of node 3. So the mutual information of the private data of node 3 is maximum. And for the rest, node 1 and node 5, it is revealed by the sum of the intermediate updates. So overall, we can see that the information leakage of the proposed approach is smaller than the information leakage of the existing secure summation approach. First, show the experimental result of the output correctness. We choose to use the Parkinson data set because it is privacy related, and here is the log likelihood of the Gaussian mixture modeling density in terms of the iteration numbers. So we can see that the performance of the proposed approach is identical at the state of of the art, which is the existing secure summation approach. So from here, we can see that the proposed approach achieves perfect accuracy. As for the individual privacy performance, we run 10,000 times of Monte Carlo simulations to generate the data, and then we use this data to estimate the normalized mutual information of unlisted node 1. Just to give one example, we use node 1 as an example to demonstrate the information leakage. So here this plot is the normalized mutual information over iterations. So we can see that for the federal setting, the information leakage is maximum. While for the state of the art algorithm, we have this information leakage. While for the proposed approach, it is lower than the state of the art. Now let's go to the last part of the presentation. So in this paper, we propose a new privacy-preserving distributed EM algorithm for Gaussian mixture modeling. It has no privacy accuracy trade-off and offers quite stronger privacy guarantee compared with the existing approach. And in this paper, we demonstrate both information theoretical and experimental validations to confirm the performance of the proposed approach. That's all. Thank you.